Hello again. This is lecture 4 in the Introduction to Radar Systems course, and it's entitled Target Radar Cross-Section. Here we have our generic radar block diagram for the 4th time, and you can see that this lecture is going to focus on the characteristics of the targets that we're going to be detecting and how they'll affect the process of detection and tracking, all the different aspects of the radar design. Okay. Now, in the introduction, we gave a quick definition of what the radar cross-section was, and also we talked about it a little bit in the radar equation lecture, number 2. I'm going to go over and just reiterate a little bit of what I said and give a more precise definition, and as I elaborate on that, you'll understand why. Now we have the target up here. We have a radar transmitter, an antenna, and the radar is emitting an electromagnetic wave in the microwave region of the electromagnetic spectrum, and that electromagnetic wave is going out, and after some distance it interacts with the target. And you can see little arrows coming off the target. The electromagnetic radiation scatters off of all the different scattering centers and the different parts of the object. And what's really going on there is we have an electromagnetic wave interacting with a big metal object, and that interaction and the fields that follow afterwards, some of it the reflected field and the field that go on, all have to satisfy Maxwell's equations, which are the equations governing electromagnetism. And we're going to look at that in detail. But later on in the lecture, we'll get into this whole issue of the scattering mechanism. But that's big picture what's happening. Now, what we'd like to do is to characterize how that target reflects to the energy to the radar by characterizing it as an effective area. And what I said earlier, and that definition is a nice broad definition that is a good one if you have a background that's, say, in history or liberal arts or the law or political science, and you're not a scientist or an engineer. It might be a good one also for someone in the biological sciences who isn't so familiar with electromagnetism as physicists and electrical engineers would be. But if you're not used to those concepts, what it is simply it's an effective electrical area that the target sees. So we want to have and that energy is that hits that electrical that area is scattered back to the radar. So you'd like to have an area dimension that when that wave, that plane wave from the radar hits the target, it's that amount of energy that power density hits it times an area that's the power that goes back to the radar. Now, if you're an electrical engineer or a physicist, you can say it in a little more, rather than 10-cent words, 25-cent words. And many will, with that first definition at that level introduced, these next set of words, if I say them slowly and twice, won't become so complicated. And I'll go over this equation, which it is in a minute, but the radar cross-section is the area intercepting that amount of power which, if radiated in all directions uniformly, that's what isotropically means, produces the same power received at the radar. So in other words, it's the area intercepting that power that came out to the target, which, if that power, that area, radiated back isotropically, it produced the same power at the radar as the actual target does. So it's a definition. Now we want to have this definition not depend on range, And it doesn't, because we have a factor r to the fourth, which takes into account that the target will be geometrically bigger the closer it is to you. So you want to have, because what happens is the power spreads out in the sphere, and it's going to intercept a smaller area. We want to have the cross section independent of the range, and this definition of a scattering cross section, as we call it, a scattering area, is independent of range because it's basically defined in terms of a power density, and that is in mathematical terms of electrical engineers and physicists, this RCS, which is the initials, the acronym for radar cross-section. We call that sigma in equations a lot. It's the limit as we go to far ranges, because we're in what's known as the far field of the radar, where the energy, the sphere is so big that it appears to be flat when it hits the radar. That flatness is we call a plane wave. It's 4 pi r squared times the electric field that's scattered by the target, divided by the electric field that's incident on the target. And with this exact definition, the scattering could go off to the sides. So the radar cross-section, you can see, is dependent on the angle that you look at the radar. And we'll look at that issue in the next view graph. And the units of the radar cross-section are an area. Okay? So I think I've gone over this definition of the radar cross-section at different levels, which I know we have an audience with many different levels of knowledge of electromagnetism, and I hope one of them settles well with you, okay, given your background. Okay. Now, what does this RCS, this radar cross-section, depend on? And I'm just going to talk about things in a general sense now, and we'll get more specific later. Well, first it's going to depend on the frequency of the electromagnetic radiation, of the electromagnetic wave, the microwave energy that's going out and bouncing off the target. Because you're going to see that that later on when we look at just a simple, if the target were a simple sphere. It's going to depend on the frequency. We brought up the concept in the introduction of polarization, the orientation of the electric field vector, and it's going to be dependent on that polarization. It's going to depend on the target's characteristics, the size of the target, whether the target's a good conductor, it's made out of metal, or it absorbs, parts of the airframe absorb electromagnetic radiation. The size, the shape, the material, as I said, and the orientation. You'd expect if you had a long cone of like a missile-shaped object, if it was pointed right at the radar, not as much area would be as intercepted as if it were traveling tangential to the radar and the radar beam was hitting the side, broadside, so to speak. And it can also depend in another way on the location of the receiver. We have two kinds of ways we can operate radars. One we call monostatically, where the transmit antenna is located at the same location as the receive antenna. Okay? And then there's what we call bistatic operation, where you have one antenna that you transmit energy out with and another antenna that you receive energy with. You remember from the first lecture I showed you that example of that World War II radar, chain home system, that had one set of towers where the transmitting antennas were located, another set of towers where the receive antennas were located. That's a bistatic radar system. There are bistatic radar systems that exist right now. Most of them are monostatic. Now you can imagine when you have a bistatic radar system, when designing that system, you're going to want to know the bistatic cross-section. That is, the cross-section not just as a function of the orientation of the object, but the orientation of the radar relative to the object, and also the orientation of the receiver. So that you're going to have to put in both of these orientations, both of these locations relative to the orientation of the target, and so therefore the bistatic cross-section data would be a lot bigger. There wouldn't be just a cross-section number when you're located here, looking nose on. There'd be a cross-section number when you're looking nose on, and different sets of angles off the side. It's another whole parameter you'd have to worry about. And then lastly, in most cases, for most radars, the radar is far away from the target, and therefore the characteristics we compare are the size of the antenna to the distance to the target. And when you're in the target is located far, far away from the antenna, we call that the far field, because the wave that hits it is effectively that plane wave that I talked about earlier. But when the target is near the radar, as it could be a missile that had a radar seeker in its nose, when that missile got up close to the target, it would be close, and it would be in what we call the near field. And the cross-section in the near field is different because the electric fields that are seen are different, because the target will see electric fields from different angles of the antenna, where they'll all appear to come from one point if it's very far away. So there's an awful lot of different factors that determine what make up the radar cross-section. Now, if you're the person who's building an aircraft, say, and you don't want someone to see you coming, you're viewed by the radar as the threat, you know. And what can you do? What can you do? Well, if you look at the radar energy that's received, this is all the factors that determine what the energy is that's received back at the radar. And the bad guys, the threat, they don't control the power of the radar. The other person does. Nor anything to do with the radar, like the gain of the antenna, its size, the distance to the target. Well, when you get in there, it's not under your control. The losses in the radar you don't have under control, and how long the radar dwells on the target to collect energy you don't. Size of the antenna. The only thing you have under your control is the radar cross-section, how big your target is. Obviously, you want it small if you don't want to be seen. So the question is, that's why it's very important to understand what makes up the radar cross-section. Okay? So we're going to look at what makes up that radar cross-section, and we're going to go through a whole set of 3 different sets of issues understanding the issue. First, we're going to look at what are typical levels of radar cross-section. Give you the ballpark, you know, how big is a ship? How big is an airplane? You know, that kind of thing. And what do they depend on? And then when we're going to look in detail at the mechanism that when an electromagnetic field hits, the electromagnetic wave composed in the electric field and the magnetic field, you know, that microwave energy hits the target and interacts with it. What are the scattering mechanisms? And what are typical contributors to the signature? That is the backscatter. Because most targets aren't simple ones, you'll see in a minute. They're very complex. And it's going to be the addition of a whole bunch of different factors from a whole bunch of different things that contribute to generate that whole radar cross-section. And then when we understand the mechanism, we're going to say, well, gee, how can we understand what it is? What's the number that comes back? And there are obviously kind of 2 things you can do. You can measure it, or you can get theoretical and develop models and predict what it is. And then you can measure it and see how well you did, and back and forth, and get good at predicting. So those are the 3 different areas we're going to go over today. Okay, next. The first thing one would want to do when one looks at how big are things is you want to look at the simplest object first. And the simplest object is a sphere. You know, you think of a sphere out there in space and a radar beam hits it. Well, you orient a metal sphere and its radius A. You know, you orient it any direction, you're going to get the same cross section because it looks the same to the radar. Okay, and now let's say, okay, we hit it with a certain wavelength. Now, if we hit it with any polarization, with the electric field going in any direction, it's going to get the same answer anyway, so it's independent of polarization too. But if we hit it with different wavelengths, we're going to see how the cross section varies if a different size of the sphere relative to the wavelength. And it behaves a lot differently in different regions. And we have three regions that basically you break things down into. Now, first of all, we're always talking in these calculations in the far field. We're far away from the radar. But we're only looking at the size of the wavelength of the radiation to the radius of the sphere. Now, when the wavelength is much greater than the size of the sphere, we're in the so-called Rayleigh region. And a British English scientist, Lord Rayleigh, did some work with electromagnetism, not electromagnetism, but scattering. And when he did that, he realized it was the interaction of light and particles, that when you took light and you interacted it with particles, that the way things behaved is they behaved in that the size of the amount of scattering you get depended on the 1 over the 4th power of the wavelength. Very strong dependence. In other words, the cross-section got bigger and bigger and bigger to the 4th power. You say, oops, that's a linear line. Well, we've got a log scale here. And here is 1,000th, 100th, 0.1, 1, and 10. And what we're measuring is the radar cross-section normalized to pi r squared, okay, which is just the area of a circle, okay, just the area of a circle. So, and then we're comparing that on this axis to the circumference of the sphere divided by the wavelength, okay, and we see as we go down here and here and here, we're going to bigger and bigger size objects. And now here's that Rayleigh region where the wavelength is very big relative to the size of what we're looking. And down in the other end we call the optical region, and that's where the wavelength is very small relative to the object. Optical, our eyes. So our eyes are up in this optical region, and when we see an object with electromagnetic radiation called light, the cross-section that we see is just pi r squared. What we see is that pi r squared, you know, when we're way out here. Funny things are happening in here. A scientist called M-I-E, he did a lot of work looking what happens when I took an electromagnetism course. The professor wrote a skull and crossbones in this area, because that's a hard one to calculate. For complex objects particularly. This is the resonance region, and I'm going to explain why. And it's because of the mechanism. The mechanism from that sphere is actually pretty sophisticated. Okay? And what we're going to see in that resonance region is there are oscillations in the cross-section, you obviously see, and the backscattered wave that comes back from the sphere is the sum you get of all the energy is the backscatter wave from the tip of the front part of the sphere, and a wave that creeps around the back of the sphere and comes back. And as it creeps around the back of the sphere and comes back, it's going to interfere constructively or destructively, depending upon, and you can see here it's adding constructively and then destructively and constructively and destructively, and then it damps out to just the optical number. Okay? And in the optical region, surface and edge scattering occur, and that's what we get. Okay, so that's you see, gee, you think a sphere would be very, very simple, but it's actually a pretty complex entity. Now, what's happening with this creeping wave? If you take a very, 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 very short pulse and you send it off to a sphere, and then look at what happens to the that electromagnetic wave interacts with the sphere. John Reinstein and a colleague were able to, and this is from a published paper that he wrote, were able to calculate what the return is from the specular, which is right off the tip of the sphere, and then that wave that creeps around the back. And for the case where the radius of the sphere is equal to the radar wavelength. And you can see this is actually the pulse shape you're looking at in each case. And the specular return is calculated, comes down right on the money as to what you'd expect it to be. So this is back, you can actually measure that creeping wave. This is an example of that. Another example which shows you that the cross-section can be very different depending on where you're looking at it. And it's an object that's relatively easy to calculate, is a cone sphere. If you take a cone and then at the back of it you make it a sphere. So you take on a cone and a sphere and you look at that, and that's a trivialized model of a reentry vehicle of a missile. If you've ever gone anywhere and see what a reentry vehicle of a missile is, they make the front part of it like a cone so that it'll go through the atmosphere smoothly. There's no big deal there. But we just put on the back of it a little hemisphere, and so it's readily calculable. And here we see this blue line and this polar plot is the radar cross section of it. Now, if we look, and here's the trajectory of that reentry vehicle sort of coming in. And in the forward direction, the cross section that you see is 1,000th of a meter square. Wow, very, 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 very small. And then as you go out an angle, and then you look at this side region here, this specular it's called, this specular region is huge. And there's a peak that's 100 meters squared when the angle is such that you're looking perpendicular at the specular region. If you're looking back at the rear aspect, you're going to see the cross-section of a cone, of a hemisphere, and at rear aspect it's 0.75 meters squared. Okay? Now here are the rings that we've marked in dashed lines are values in cross-section relative to 1 dBsm, relative to 1 meter squared, and they're marked in dBs. So this is really a log scale, and each ring of the circle is an order of magnitude greater in cross-section. Okay? So you can see that this 100 meters squared is almost 2.5 orders of magnitude more than over here, than this point in here. 1, 2. Okay? Excuse me, this part in here. So what you basically you can see is the huge difference in cross-section. Okay. Now, for some typical objects that you might think, say, okay, how big is a helicopter? How big is a boat? How big is a man, a bicycle, a bird, an insect? And these are well known and documented in many different radar introductory texts. A simple single-engine aircraft that an air traffic control radar would like to see is about 1 meter square is its radar cross-section. A 4-passenger jet, 2 meters squared. It's got some streamlined paths to it. A jumbo jet, like a 747, 777 or something, 100 meters squared. Jet fighter, 6 meters squared. Small open boat, 0.02 meters squared. Probably a 20 to 30 foot small pleasure boat. Okay? A good-sized cabin cruiser, 10 meters squared. A ship with 5,000 tons of displacement, huge, 10,000 meters squared. Truck or automobile, bicycle, a man, about 1 meter squared. Birds and insects, very, very small. But we're going to see later lectures that in your radar coverage you can have millions of these, and they can add together in flocks to give sizable cross-sections which can be seen by radars. So we'll put them down there too. But they vary all over the place, the cross-sections do. Well, welcome back. This is part 2 of the Target Radar Cross-Section lecture. That's lecture 4 of the Introduction to Radar Systems course. Now let's look at what contributes to the radar cross-section. What are the scattering mechanisms that there are? And how do they contribute? Here we've got just a generic air-breathing vehicle, I'll call it. And it's got all kinds of stuff on it that you'll find on most things that fly in the air. Some objects that radars see have fewer, but this has got them all. And it's a good example. And probably not many have all of this stuff. But it's a great way to look at physically what are all the different things that can cause backscatter. Okay? And then we're going to get into the physics of what's going on a little later. This is, you look at the object and what does it. Okay? And if you look functionally, they divide up into 3 areas. You can get backscatter from the structural system. The vehicle or the target can have wings, control surfaces that help you to fly and turn your aircraft. Okay? It's got its body shape. It could have a blunt nose, a round nose, a tipped nose. It could have a circular or a triangular cylindrical shape. It could be square. There are control surfaces like the elevators on the backs of wings. That's the structural stuff. Then there's the stuff that gets you from here to there, the propulsion. You've either got propellers and engines, or you've got an inlet where you're going to let air in for a jet or a ramjet or a okay. And you've got, if something is looking at the back, you've got a tail end where you'll have exhaust coming, an exhaust port. Okay. And then we've got avionics, stuff that helps us get from here to there. We could have a seeker, which is a sensor, which, well, it wouldn't be covered by metal here. There'd have to be an opening for an antenna for either an infrared or a radar system, and the radar energy can get in there and scatter back. So we've got that. We've got antennas for maybe a GPS system on the air vehicle, or communications. It could have an altimeter if it's a single-engine aircraft and little wire sticking up. That's going to be the altimeter wire and stuff that sends a beam down to the ground. So you can have fasteners that connect one stage of a missile to another. You can have the shape of the missile be a cone and then go to a cylinder, so there's a discontinuity. There can be grooves where the stagings begin and end. Every one of those things that I talked about, when that plane electromagnetic wave hits it, it's going to interact with it. And what's going to happen is we've got to satisfy this stuff called Maxwell's equations. And now's probably the best time to bring it up. And that is back in the 1800s, there's this guy named James Maxwell. I just have over here I can just see it from where I'm looking. I have 2 copies of copies. You know, they were printed in 1960 of his 2 volumes where he described the theory of electricity and magnetism. And he came out with a set of equations which link up how electromagnetism works, the theory of how that stuff works. And that the electric energy is coupled to the magnetic energy. And whenever you have the interaction, particularly of an electromagnetic wave And metal, this metal object, you have to satisfy Maxwell's equations. And that satisfying of Maxwell's equations was what causes the reflection. And so what we've got to do is solve Maxwell's equations when this electromagnetic wave hits this beast. And there are all kinds of things that happen. Now the first thing is that, and it's probably the easiest way to see it. We're going to talk about it later, but I want to just bring it up. Sometimes it's nice to tell you again, and then remind you what I told you when I'm coming through with a concept. Maxwell's equations tell you such things as you can't have an electric field inside a metal. But when you come up to this metal and this moving electric field hits it, in order to satisfy Maxwell's equations, you generate currents on the surface of the target. And to cancel, and those currents create, those induced currents, they're called, create fields in the opposite direction so that on the surface of the metal, in the metal itself, you don't have electric fields, because you can't. So that Maxwell's equations is satisfied is a nice way of saying it. And so these induced currents generate themselves electromagnetic waves, and they're the reflections that you see back. But you've got this very complex object with all these things going on, and the electric fields, an electromagnetic wave interacts with all of these different body shapes, control surfaces, inlets, exhausts, seeker ports, fasteners, differently, and they all add up together, and they give you the sum total of the electromagnetic energy back. So what you're going to see is there's a huge volume of knowledge in mathematical engineering and physics that has gone into understanding how to do these calculations. And we'll get into them later. But the point is, what we got to do is we got to satisfy the laws of physics, Maxwell's equations, to get. That's the big picture. Now, let's move on, and we're going to move on nice and slowly so you see what's happening. When I give you an idea, I'm going to show you some movies now on the interaction of simple electromagnetic wave with simple objects to show you these different effects. Now, I've explained to you physically like what they are on top of for that preceding air vehicle, but you can break down really into three categories the kind of interactions that you have. The first one is you hit a flat surface, like when light hits a mirror, and it reflects right back. And we're going to look at the case. The first case is when a specular reflection, when an electromagnetic wave, and we're just going to look at the electric field part of it. It hits a flat plate, and it bounces. We're going to have other effects we'll look at, but the main effect it's an example of is specular reflection. If you have an electric wave, it hits the plate, and here the electric field, this X means the electric field is in the down direction, the magnetic field is going in this direction, and the direction of propagation you'll see in the movie is going in that direction. It's going to bounce back. We're also going to see diffraction effects, and I'll talk about them. The next case is when the same kind of an electric field comes in at an angle, and from your feelings about light, you're going to have a wave coming off, bouncing off. But also you're going to have the wave propagate down the path. Particularly the first part of the wave is going to hit right here, and you're going to see what we call leading edge diffraction. That is, at the leading edge of a wing, you're going to get a reflection. Then when we change the polarization, the wave will go down, and you'll have, at the end of the wing, a trailing edge reflection. Then we're going to look at a cylinder, and when the wave hits it, we're going to see a specular coming off the cylinder. But if we change the polarization, we're going to have the creeping wave come around. Okay? And you're going to see that creeping wave effect. And then lastly, when we send a wave into a cavity, like a rocket motor or a cockpit, or roughly speaking, or the inlet it's a very good reflector. And if the energy goes in, unless you have a lot in here to absorb it, energy's going to come out. And one of the properties that you end up getting is an entity called a standing wave, where there'll be energy that will just stay there, but energy will be reflected back and you'll see it. So I'm going to go through these one at a time. I'm going to show you videos that last maybe 10 seconds or so, and I can click on them again and you can see them and we'll talk about them. Let's look at the first case. The first case, the phenomena we're going to look at is specular reflection. Okay? Now, these have all been generated with a calculational technique known as finite difference time domain simulation. So it's a way of propagating electromagnetic waves and having them interact with conductors and things like this. That's very simple. And it's scattering by a strip. It's a Gaussian pulse that's incident on this strip, 4 meters long, and the width of the electromagnetic pulse is 0.5 meter. And the E-field polarization is in the Y direction going into the screen that you're looking at. And the phenomena we're going to look at is specular reflection. And here's what you're going to see. The red is positive and the blue is negative. And this is what it's going to look like in time sequence of photographs. You're going to see the wave come in. When it gets to the strip, it's going to create those induced currents in the opposite direction, which will create opposite electric fields. And you'll see the field go back out, and that's the reflected wave going out. Okay? But also you see energy coming off the rear. And we'll talk about that later. Okay, now let's go, and as if I click on it, here you'll see the movie. It takes its time, but it comes in. And here's the electromagnetic wave coming in. And now watch what happens when it hits the metal strip. Can't have an electric field in here, so we have to generate some induced currents. They're induced. Bingo! They generate an electromagnetic field. Okay? And that's the reflected specular. But notice that some of the energy is behind it. That's that in the propagation lecture we talked about diffraction. How some of the energy can go behind an object. I'm going to go through this one more time so you can see the diffraction, where it's going behind the object. Okay, let's do it one more time. Now this time I want you to focus that the red, the energy, not only comes by it as you'd expect if it were light, but and the wavelengths weren't the size of the object. You're going to see some of this red energy go behind here. And that could be like energy going behind a hill. If a radar beam hit the hill, this was all perpendicular. If that plate were perpendicular up and down, there's energy behind it. And that's called diffraction, where the electromagnetic beam bends around it. Okay? Now we're going to look at leading edge diffraction, where the beam comes in and will hit this leading edge and will generate a backscatter at this leading edge. And you can see the beam coming in, hits it, and creates. And also you have the reflected beam up here too, as you'd expect as it hits. Okay? But coming in the direction of where you were, you'd have the radar back up here. This is the leading edge diffraction that will come back to you. Okay, now let's look at the beam come in. And this is the leading edge diffraction. Bingo! The energy will come back, but also we've got this reflection right back here, where the beam reflects off, but at an opposite sign of the electromagnetic field. And we also see very little interaction at the back. To let you know how this is the polarization dependent, that's where we had the polarization going in one direction. Now when we change the polarization, we'll get trailing edge diffraction. Now a lot of radars use radiation that's a mixture of linear polarization. Excuse me, the best way to say this is what you saw was a radar that was linearly polarized and exactly perpendicular the electric field was to the plane. It was vertically polarized, perfectly relative to the wing surface. If the plane had been diving a little bit, you'd have a little bit of each kind of relative polarization, and you'd get some leading edge and trailing edge, which you get most of the time. But now when we have the magnetic field coming out and the electric field in this direction, okay, now we'll see what happens. And we'll see we're going to get at the trailing edge. We'll get the deflection. We'll get the diffraction. We'll get the reflection back from the trailing edge diffraction. You see a little bit of leading edge, and here we see the behind the plate we see energy, and at the tip we see energy coming back to the radar. Interesting. So we see the electromagnetic energy does not stop by the barrier, it continues on, and that's diffraction around the plate. Okay? Now let's look at specular reflection when we send an electric field that's along the line of an infinite. It's a long, tall cylinder. And here's what we see. We see again a specular reflection going back to where the radar beam came from. And this again is for one polarization. We'll get the specular, and if we change the orientation of the electric and the magnetic field, we're going to get a different phenomena. What we saw just there was a specular coming back towards the radar. Okay, let's look at it again. The electromagnetic wave coming in, and we want on the cylinder the zero current, and we generate the wave coming back. That's an example of specular reflection. Okay. Now if we take an example where the magnetic field is plotted into the paper and the electric field is out this way, we're going to see a creeping wave go around, right around both sides and come back out. And you're going to see here's the wave, and notice here, what happens is the wave goes around the back, and when it gets to the back, it comes back out, and what we see coming out in this right region here is a wave that comes back around and will interact with the wave that goes back, producing a creeping wave. You see where the wave is, the scattered part, and then after the scattered part goes out, we see there the creeping wave coming around and being generated. Weaker, of course, but that'll go back. But it's an example of it. Okay? And lastly, we're looking at simulation of scattering by a cavity, and the phenomena we're going to look at is a standing wave. And here we have a frequency of 300 megahertz. The wavelength is a meter, and it's a 2.5 meter deep cavity, 1 meter wide. So there's a resonance here. The wavelength is the size of the cavity, and it all resonates very nicely. And you see the wave come in. And what we're going to look at later on is this is the how shall I say it? After this point, what we're looking at is the sum total of the wave coming in and the wave bouncing back. And you'll see the standing wave build up, and then you'll see it generate energy back in this direction, the standing wave in the cavity, and then in these last segment we subtract off the input wave so you can see what's happening over here. This is just the scattered part coming out, not the scattered plus the incident. It's a little more complicated. So we have the wave coming in, the positive, negative, and you see after a while the standing wave building up, and then after it builds up you see the burst of energy coming out, and so this cavity reflects back quite solidly. And now if we just subtract off what comes in, you see that energy is coming out of the cavity very efficiently and moving back. So cavities are a no-no. And now we'll move on to part 3 of lecture 4 on radar target cross-section issues in the Introduction to Radar Systems course. Now the question is, how can a target cross-section be determined? First one is by measurement. You can build a full-scale measurement range where you take and you put your object, in this case they look like they're missiles. You have a full-scale missile and you put it on a pylon. And I'll get into what you make the pylon out of so it doesn't interact with, you're not measuring the pylon. Then you can make scale model measurements. And the second part is we can do predictions. Now what you do typically is you'll take the target. In this case this is just a photograph of a fighter, an F-16, and it's just on top of a pylon. We placed it on top, and the pylon you make out of dielectric foam, very close to the dielectric properties of free space. So effectively it's structurally sound, but it's on a solid pedestal, but electromagnetically the electromagnetic wave that hits it won't see it. You can mount it on a metal pylon, and what you do is you shape that pylon to reduce its cross-section and make it very small. You can have just a sharp leading edge and do whatever people need to do to make that very low reflectivity. Or you can make your measurements without the pylon, with just the pylon and no target, and subtract off the background, which is just the pylon, from your measurements, and that indeed would be then the measurement of the target. It's sort of target plus pylon minus pylon cross-section equals target cross-section. That's how full-scale measurements are made. Now this is measurements at a full-scale range facility called RATSCAT of a Johnson generic aircraft model. It's a simple full-scale model that has many of the different features that aircraft have, like a nose, a cylinder, wings, and control surfaces, and this was taken with vertical polarization on transmit, vertical polarization on receive, and targets at an elevation angle of 7 degrees, and the radiation used was X-band, 9.67 gigahertz. It's about 3 centimeters approximately. And here we've plotted the radar cross-section in dBSM, which is meters squared in dB units. So this is 1 meter squared, 10 meters squared, 100 meters squared, 1,000 meters squared. And we plot it. 0 is nose on. Here is broadside. And here's the tail. Here's the other broadside and the other tail. plus or minus 180 degree aspect angle as we swing from the tail all the way around 360 degrees to the nose in the center, and then the tail over here. Now let's just start at the nose, okay? We get to the nose, and that's a very, very, very small scatterer. The nose is, the size of the scatterer has to do with the radius, and if you make it a very sharp tip, the radius of the ball that effectively is related to it, so that you get a very small cross section there. And then as you sweep around, you're going to see a set of surfaces that are going to come into play that we've talked about before, okay? And they're going to be when something is either we've got an edge that's going to give us some cross section like those leading and trailing edge scattering, or it's going to be a broadside effect, okay? So as we move off, the first angle as we move off 0 degrees that hits us is this trailing edge of the wing, believe it or not, okay? And right in there is 0, and the first bump we see is the wing trailing edge. And then as we move over in angle, then the leading edge, which is bent back a little bit more than the wing, okay? And so this is the most perpendicular thing as we go from nose on, and we're looking at the whole plane. This is the next most perpendicular is the wing leading edge. Then we move quite a bit of angle, and you can see here around 70 degrees is when we're 70 degrees off of the nose. The specular of the cone, of the nose cone, comes into play pretty big. And then when we get 90 degrees, we get a giant specular from the fuselage. That's the biggest thing. And then things drop down, not pretty boring, and then we get, on the back of this there was an end cap. So we see an end cap on the back of the missile. So you can see those physical effects taking place. A little later when we do some calculations, we'll put some calculation numbers over this and say, how good were we relative to real measurements? We've just looked at full-scale range measurements. Now let's look at an example of what compact range measurement techniques are like. Here we see a photograph of a U.S. Navy compact range. And below it, this Navy range is at Point Mugu, California. And below it is a schematic of a compact range at the Air Force Research Laboratory at Wright-Patterson Air Force Base. You can see that in both cases, the target, in this case, both are air-breathing vehicles, a fighter, and a little hard to tell on this one exactly what the object is. But they're located on low RCS pylon support systems, and they're inside of what would appear to be a very large box. Surrounding them is absorbing material made of carbon that absorbs any reflections other than the angles you're looking at. The mechanism of generating the electromagnetic plane wave is shown here. We have a parabolic feed, and it sends energy to a subreflector, which is typically at the Air Force compact range is below ground. And then the energy goes up to a subreflector, and the shaping of the main reflector is such that the electromagnetic energy that's sent out is a plane wave. The shaping of the reflector sets it so it's a plane wave going out, hitting the target. Okay? Now, there are a number of reasons you want to have these compact ranges. The first of which is you can operate them in any weather inside. And it's under very nice controlled conditions. And you can also use these compact ranges on subscale models. And it's a technique that is used quite often to make RCS measurements. because the full-scale measurements in many cases can be quite costly when they're done on a big, complex range. And you can have multipath effects, which the absorbent material around the compact range mitigate. Okay. Now we have we can do things with scale models in small ranges. Okay. Now here we have a drone, and it's at a 0.29 size, so you don't have the whole plane, or you have a model of it. You can make calculations, you can make measurements on scale models, but you have to scale things, and I'm going to go over how you do that. So if you're at full scale and you want to make a measurement at frequency f, and you scale down the size of your model, reduced size, you divide it by, say this S with 2, half size. In this, it's a 30th about, so S is a 30th for this guy right here. And in the subscale, you make those measurements at a frequency S times the frequency you want to know the data for. And then you've got the right frequency. But that's part of the problem. The next thing is, how do you scale the other factors in the target? Well, length scales the same. Length is fine. You scale the time so that the times you look at of the pulse width and things like that, you make them shorter. As I said, you make the frequency longer, the wavelength shorter, and then the permeativity and permeability, which are the dielectric and magnetic properties of the material, are the same. But this thing called conductivity, which is sort of a measure of how good a conductor. If the material isn't a perfectly conducting metal, it's got say it's a composite, something that's got loss in it or something, then you've got to scale the conductivity of those entities that are on the object. And this is interesting because sometimes what you've got to do is, when you do the scaling, it gives you a conductivity for which there isn't anything around, and you have to invent a new material to make it. But anyway, those things can be done. And what you end up with is a cross-section, which is the real cross-section divided by your scale factor to the, your measured cross-section is your real cross-section divided by the scale factor squared. So you'd have to take your scaled cross-section, multiply it by S squared to get your full scale cross-section. Okay? And now I want to go back to that whole issue of scattering, and we went over a little bit before. Remember I said I'm going to tell you once, going to tell you twice, blah, blah, blah. Now that we're in a minute, we're going to go over a couple of examples of how calculations are made. And I can tell you this next 2.5 view graphs, books are written on. We could talk about this for days and days. It's such a complex topic because it is mathematically so, what's the word? It's just an awful lot of mathematics, and it's tough. Even when you get because we're taking Maxwell's equations, which look simple, but when you want to have those Maxwell's equations calculate the cross-section for a very complex target, it gets very complicated to do that calculation accurately with even today's computers. So we're going to go over a couple of the scores of methods that are available to give you a feel for what people do and what are the strengths and weaknesses of the different methods. That's appropriate for this kind of a lecture. Okay? So we have the plane wave coming in, and we've got to satisfy Maxwell's equations. And what happens? Well, the plane wave interacts with this complex object. Let's just, for simplicity's sake, it doesn't have conductance in it. It's just a pure conductor. But it's very complicated in shape. And what you do in order to satisfy Maxwell's equations is, it isn't what you do. What nature does is surface currents are induced. And these surface currents vary in time as the electromagnetic and magnetic fields come over the surface in time. And so the currents that are induced change with time, and whenever you have currents changing with time, you generate electromagnetic waves. That's what Maxwell's equations tell us. It's like you either have a current or an accelerating charge that changes with time, and you generate an electromagnetic wave. Well, when you induce currents on the surface of this object, you're going to generate electromagnetic waves, and they are the scattered energy that you see. And we want to measure that scattered energy and see how that compares to the incident energy, the power. And then you remember the definition of the radar cross-section. It's 4 pi r squared, and the limit of long distances, the scattered electric field squared over the incident electric field squared. Okay, and so in order to get the RCS, the sigma, the cross-section, you've got to know the currents everywhere, and then from those currents, you have to satisfy Maxwell's equations everywhere at the same time. So not just, Maxwell's equations have to be satisfied during the scattering process in order to generate that, solve the problem and get the RCS out. So it's a very complex problem. And we have a lot of different prediction approaches, and I'm just going to go through a few of them. And as you can imagine, they divide up into different methods. And there's a high-frequency approach, and one of them, one of the more sophisticated ones actually that's used is the physical theory of diffraction, where you generate currents, and you add on currents on the object as a whole, and then you look at diffraction and edge currents and add those in, and then you solve Maxwell's equations, solving these integral equations. It's computationally, it's relatively easy to do. It's good for arbitrary complex geometries, but there's no free lunch ever in this business. It neglects some of the scattering effects, and like diffraction, I'll give you an example. Say, for instance, the wave comes in, it hits this wing, and then bounces off another wing. The interactions it doesn't handle well. And it's applicable only to large, smooth geometries. So it's got, and some of those scatterings, so it's got stuff that has issues with it. Another method you can do will give you the exact answer. It's called the method of moments. You divide the whole surface up into little sub-pieces, and you want each one to be about 1/10 of a wavelength in size, 1/5 or 1/10 of a wavelength in size of your radiation. And if you've got an object that's 30 meters long and a very small 1/30th of a meter is your wavelength, you've got a very large number of objects. Okay, so you can do an exact formulation of what the answer should be down to, if you crunch enough. But you've got what you end up doing is change it into a set of equations that have to go in, and you have to invert matrices, and you go wacko with the computational intensity to get the accuracy you want. There are a whole bunch of different codes that are out there. Here are some acronyms for some of them. Yeah, but it's computationally very intensive. And the more precise your model is, the number of these are called facets, the greater the number of facets, and it goes up with powers, I think squares of, since it's an area issue, it'll go up as a square, and that's got some issues with it. Now when we run the physical theory of diffraction predictions up against our RATSCAT measurements, and in red we see here, the physical theory of diffraction. You can see it pretty well is predicting the location of each of the peaks. But the areas between the peaks, here and here, it doesn't do too well. And that's where there's different interactions going on. And this is at a good high enough frequency that this should be good. So it turns out that some techniques work well to get some parts of the cross-section, other techniques work out for others. So now I'd like to, in this last view graph, go with just a simple, what we call a stoplight chart, where we'll say, hey, yeah, it's good, no issue. Yeah, there's some issues. Yeah, there are big issues with this. So we're going to look at, first, if we want to get, for things that are, say, 3 centimeters, air vehicles, we want to measure them. We can measure full scale and subscale, and we can predict them with the high-frequency methods, like the physical theory of diffraction or method of moments. And how good are they at dealing with calculating the body cross-section, the surface details, and taking care of other issues, and what do they cost, you know what I mean? Okay, well, full-scale measurements give you what you want, but they can be very costly. Enough said. There's some significant issues of getting all your data with cost. You'd like to be able to crunch it at a computer and get the answer out. Okay? You'd like to be able, and of course when you make a measurement, you're making it at one angle, one polarization, one frequency, one this. With a computer, if you could do it, you just change the frequency, calculate it. When you do subscale, that'll handle the body shape, the details, and the inlet exhaust. I mentioned we've got this issue with materials. If the aircraft isn't pure metal, it's got composites in it, or stuff with conductivity. You've got issues you've got to deal with. And the antennas and how you deal with the antennas, you have to make a subscale model exactly of the antenna that's inside a radome and stuff. And that can get from red here to yellow. That's an issue that's down in this end of things. In terms of predictive methods, the high-frequency methods are very good on body shape, but on surface details and antennas, they're a problem. And there are moderate issues with inlets and materials. Now, relative to prediction with the method of moments, body shape is a real issue because if it's got complicated body shape, you've got huge numbers of facets. But it can take care of surface details very nicely. Inlets and exhausts are a big problem because of the facet issues and modeling them. The materials you can handle quite nicely with this method, and the antennas are a moderate issue. So you can see and cost. There's no green here anywhere because if there was, you'd go that But the point is, you get some of the stuff one way, some of the answers one way, and some the other. Okay, now I'd like to summarize. The radar cross-section we see, it varies all across the different targets of interest, and it depends on a lot of different stuff. The target characteristics and the radar parameters. Target characteristics like the shape and material, depends on the radar parameters like frequency and polarization, etc. like that. And there's all that I went over very carefully, the different contributions. The structural composition, like body shape and surface details, they're going to contribute. Propulsion and avionics. Propulsion, that's with the inlets and exhausts, engines, stuff like that. And in the avionics, you're going to have stuff help you fly the plane, like antennas from radars or communication antennas, and seekers in missile heads and stuff. All those kinds of things you've got to take, and they'll give contributions. And the best way to get your estimate of the target signature, i.e. its radar cross-section, is to use multiple tools and roll them up together to get the best signature. Okay. Well, thank you very much for your time. It's the end of this lecture.